Okay. All right, so tonight is a very important class because this is a really hard topic, and you have to understand this stuff. You can't just look for a set of procedures and then when you get a problem, figure out which procedure to apply. It's just not going to work because they're all different. And then on the exam, there's going to be some applications that are slightly different, like a different realm. Okay, but all the principles are the same. So you have to approach these problems with the intent that you're going to understand what's going on rather than memorize a procedure, okay? If you're just out to memorize a procedure, you're going to be dead. Okay, so here's the deal. Whenever you're doing work, how do we calculate an amount of work? Well, that's in generally correct, but work is going to be the sum of little bits of work, right? If we want a volume, we have to sum up little volumes. If we want an amount of weight, we're going to sum up a bunch of little amounts of weight. If we want work, we got to sum up a bunch of little amounts of work. That's what that means. S for sum, integral means S, German S for sum, a bunch of little amounts of work. So that principle is huge. So then 80% of doing this problem is then figuring out a typical little amount of work. So that's where the force times distance comes in. So a little amount of work is going to be force times distance of some element that we're able to calculate a little amount of work. So the whole point of these problems is you can't do it as a big lump sum. Why? Because either the force is changing across what you're doing or the distance is changing across what you're doing, so you don't have a constant force and or a constant distance. So in this, we've got the pool. We're going to empty the pool. And it's what? Mine is 4 meters high. The water is at 3.5 meters. So, why do we need an integral? Is it because the force changes or the distance changes? Right, so what we're going to do is we're going to calculate a little bit of work we're able to calculate a little bit of work for one layer of water. Because at one layer of water, the distance it has to move is all the same for that whole layer. We can't do a column of water, right? Because at the top of the column would have a shorter distance than at the bottom. So that doesn't make sense. So when we do our little bit of work, it has to be something for which neither the force nor the distance changes so that we can actually do it. So we're going to do one layer or a pancake of water, and that could be at any depth. That could be at any depth. So that's right there. And so we call that depth. It's going to change, right? We're going to have all the layers starting at the top layer down to the bottom layer. So that distance that it has to move is going to be x. It's going to change depending on which layer you pick. Okay? So what is the force of the layer? What is the force for a single layer? So we just get really this. What's the force equivalent to? What's the force to lift something? That's what we're saying. We're going to take that one layer of water. We're going to lift it a distance x. All right, so the distance that we're going to lift it is x. So what's the force required to lift something? It's weight. It's weight. The force required to lift something is its weight. So, and that's going to be found by, what we got, we're in metric here. So the force is going to be its weight, which is going to be mass density, which would be we got kilograms per meter cubed. So what is the force or the weight unit in the metric system? You got to know that. That's newtons, okay? So we got 1,000 kilograms per meter cubed. What we really need is weight density. So what's the weight density if it's 1,000 kilograms per meter cubed? Yeah, so this is in kilograms. To get newtons from kilograms, you're going to multiply by 9.8. And then you get 9,800. Now this is weight density, newtons per meter cubed. So the force is going to be the weight density times what gives us newtons. What quantity times newtons per meter cubed will give us newtons? Volume. So the force, the weight of this thing is going to be the weight density per meter cubed times the volume. So this little amount of work is going to be the weight density times the volume of that thing times the distance we have to move at x. It's going to be rho vx. So we got our rho, our weight density is 9,800, so now we just need the volume of this thing, which is what shape? Not a circle. Circles are two-dimensional. Cylinder, it's a cylinder, so it's going to be pi r squared h. And then we know we're going to have times x. Question?
What does the P stand for?
Rho. It's Greek rho, density, weight density. It could be a mass density, but what we're going to need is weight density eventually. So rho is density. Okay, so then we're almost there. We got, what's the radius of this? My radius is 10. These are gigantic swimming pools. Did you think about this? 20 meters across. It's like 65 feet. Okay? Okay, and then what is the height? What is the height of this element? Right, it's got to be so thin so that it's virtually all one height, right? Because if it's significantly thick, then the top water has less work, and the bottom of the layer has more work. So it's got to be like we just virtually no thickness, right? There's just a very small amount of thickness for which we can consider one distance that's all going to move, right? So pi times 10 squared times delta x times x. So here is this is the weight of our layer, force, weight, times the distance it has to go. So that is our little bit of work. I know that lots of students, they don't want to do this little bit. They want to go starting to write integrals. And I've been trying to encourage you for the last 2 weeks. Start by writing the formula or the expression for the little bit of whatever you're totaling up. In this case, a little bit of work. Okay, so now we're ready to, so that's all the setup work. And that's, like I said, that's 80% of it. It's getting that. So now the total work is going to be the sum of all the bits of work. So it's going to be 9,800 pi 10 squared x. Now we've got like ultimately thin layers, dx. And so then what is this? This is from what x value to what? So the first layer down to the last layer. So if the total depth is 4.5 and the water is 3.5 high, then where's the first layer? What value of x is the first layer? 0.5 is your first layer. That's how far the first layer has to move, the top layer. Right? The top layer, we got to move it up 0.5 meters all the way down to, so x is going to then vary from 0.5 all the way to, the last layer has to move how far? 4. So that's it. Okay, and then if we want to do part B, it's basically the same thing, except we've got 1 meter more to move all the water. So if it's a 1 meter outlet over the side, so a spout or something like this, that's 1 meter more. So now the top layer, so this is part B, the top layer has to move. So it's the same layers, they have the same weight. And they're going a distance of x, but it's now just that those x's are different. So it's going to go distance of x. This is part B now. So now the top layer has to move how far? Yeah, so before it had to move 0.5, but now that top layer has to go an additional meter. So it's going to go, the top layer has to move a distance x of 1.5, and then all the x's in between. The last layer has to move a distance of 5. So for part B, all you'll have to do is change the limits of integration. So this is part A here, and these are super easy integrals. Question?
So I was working with
Yeah.
today. The way that they had to do it was they manipulated the x value. So it would be 0 to 3.5, but it would be, I think, if it's 4 meters high, then it'd be 4 minus x. Instead of doing like the correct.
Yeah. So well, yeah, because now they're putting their x from the bottom up.
Oh, okay.
So they're saying the x equals 0 is the bottom layer, right? And then x is going up from the bottom. That's all they're doing.
Okay. I was just wondering if that's like the correct, like, if there's a better way to do it.
What do you think?
You're right.
I just think this makes more sense, right? I mean, it's easier. So sometimes you have to do that. You have to look at 4 minus x or whatever. But it works. I mean, whatever makes sense to you. But you don't have to do that 4 minus x thing, right? So if you do it down from the top, then your first layer is at x equals 0.5, and your last layer is at 4. Then you don't have to worry about the 4 minus x or any of that. So if this, I think this, I try to always do it the most efficient way. But there are different ways to do them. Yeah?
So on the test, are you going to care how we get to the answer? Or, because I mean, you can use physics formulas too to do some of this.
No, I want to see that you can set up integrals. Yeah. And that be, like I said before, I'm going to give you something that is going to be a new context. It's going to be something other than work. But again, it's going to say, find the total what? Find the total amount of widget, whatever that is. And so what are you going to do? You're going to calculate what? A little bit of widget, right? And then you're going to sum up all the little bits of widget. That's the point. This is the principle that you have to have. And so then it's just a matter of coming up with one typical amount of a little bit of whatever you're calculating the whole of. So look, the dx is not there just to say, oh, it's an integral, so we need to plop a dx at the end. No, look, the dx was part of the volume. The dx was actually mathematically part of what's going on. It was part of that volume and therefore part of the weight. So that dx is not just an afterthought. It's part of the math. The dx, along with the rest of it, gives you a little amount of work. If the dx wasn't there, you don't have a little amount of work. You have something else. But with the dx there, now that whole thing is a little amount of work. And we saw it came right there in the volume and the weight. Okay, it came right from the volume and the weight, the thickness of your layer. Other questions? Okay, so let's do more. We'll spend the whole night doing more of these. And then what we'll do is we'll start new material on Monday, and we'll have our exam Wednesday. But the stuff from Monday won't be in the exam. So this physics stuff is the last stuff on exam 2. It'll be a week from tonight, okay? But then Monday we'll start new stuff, which, did I say it was Monday in the syllabus?
I thought the test was on Monday.
Okay, well, you're happy. That's what's important. Is this a better plan?
Wednesday, yes.
Yeah, that way you can take advantage of office hours, getting help Monday and Tuesday. Okay. So for Monday, there's another 4 or 5 web work, but then we'll have a pretty significant. We gotta have more practice of these. So there's going to be a written assignment, and so that will be the majority of the assignment. You'll have like I think it's four web work problems, and then a more significant written portion. Okay, but you gotta have practice because they're all different. Okay, so let's do. What should we do here? Let's do a trough problem. Yeah, sure.
Are you going to post like your review guide with topics again, or is it just kind of like we haven't covered too many different topics?
Yeah, so it's all the applications of integrals. So it's yes, I will, but it's the volumes of revolution and the other volumes, arc length, and this physics stuff is the majority of it. Yeah. Okay.
Professor,
Yeah.
will there still be conceptual questions like how was in the last exam where you asked us like the big ideas?
Yeah, I mean, I think solving these problems requires that anyway.
Okay.
So, yeah, I mean, you got to understand what's going on to set up these problems. So it's just, I think it's more just inherent in these that it's not like one or the other. It's just all together. Okay, so let's do this here. We got a horse trough. Okay, going back like this. That's like for water or something, for a horse. And let's say it's half full. I'm not having my best night drawing here, but you got the idea. So that's half full of water, and let's say that the height of it is what is that? 20 inches. And the length of it is 52 inches. And at the bottom, it's 27 inches, and at the top, it's 32 inches. And so we want to find the total work in joules. So you get all the water out. And what did we say? The weight density of water is 64 pounds per foot cubed. So we said last time? 62.5. Okay, so I have some work to give back to you, which I forgot. My office is close. So I'm going to go run and get it while you're busy working on this. Game plan. Total work equals? Sum of, so that force times distance. It's the sum of a little bit of work. Little bit of work is? That's our force times distance. Okay, so what's happening on this one? So distance again. So we want to go take it from where we have to raise all our layers to. Call that x, right? So that's the top. So we've got to move all these layers a distance of x. But what's different about this one than the circular swimming pool? Okay, yeah, so the width of each layer is different depending on x. So not only is the distance going to be x, we know that, but then the width of our layers is going to depend on x. When x is, what, this 10 inches here, you're going to have the widest layer. And then when x is 20 inches, or the equivalent feet, whatever that is, you're going to have the skinniest layer here. Okay, so force is going to be weight density times volume. And that's our 62.4. 0.5, is it 0.5? Pounds per foot cubed times, what's the volume of this thing? Or of our typical layer? Yep, base times width times height. Okay, so we got the weight density times the volume will give us pounds. Pounds times the distance it goes. Okay, so now the what do we know? We know the height is what? Delta x. And what are we calling the? So let's call this the width. So then I guess this is the base here, or maybe this is the length. Which is the length, the long way. Maybe makes a little more sense. What's the length? Let's get this in, and I'll start moving things to feet. We're going to need feet, right? So how many feet is 52 inches? 4. What is it? 4 1/3. 4 1/3. 13 thirds. 13 thirds feet. Let's keep it exact. So all that's left is the width of this thing, but that width is a function of x, right? And what did we say last time? Linear relationships are key in these problems. So here we've got one. So the question is, we need, for a given x, we need to make a relationship that for a given x delivers us the corresponding width. Okay, so when x is at the top, or let's do the bottom first. So when x is the full 20 inches, which is 20/12, what's the width? 27/12. There's one ordered pair. Given an x of 20/12 feet, then the width should be 27/12 feet. And then what else do we have? We know that when x is 10/12 feet, what should the width be? Split the difference between these two, right? It's going to be halfway between 27 and 32. 29.5 over 12. So maybe it's easier to just do this in inches and then divide by 12 at the end. It doesn't matter. So you could do this in inches first, get this relationship in inches, and then just divide by 12, or we can just work with feet. So we've started working with feet, so we'll just keep going this way. So we've got two ordered pairs, x comma w, x comma w. So what we really want is what's the w for any x. And so that means making the equation of that line, or the linear relationship. Given an x, it spits out the corresponding w. Okay, any questions so far? And that expression will be our w in terms of x. It'll go right there, and we'll have our typical amount of work. Questions so far? Yeah.
Can you repeat how you got 29.5?
So because I told you it was half full.
Okay.
These are flat linear sides. It's halfway between 27 and 32.
Oh, okay.
So it's the average of 27 and 32.
Right.
Yeah, sorry, we did do that fast. Sorry. Okay, so then we need the rate of change, or what you think of as the slope. So we could do W2 minus W1 over X2 minus X1. So I'm just going to be, we don't need all the 12ths to do that because they'll just cancel out. 29 minus 0.5 minus 27 over 10 minus 20. So dividing by 12 on all of these, we'll just keep that ratio the same, okay? So what is this? 2.5 over negative 10. Negative 0.25? Do we have a few people to confirm that? So that is our what? Width per x. So W, this is our W per x slope or rate of change, however you want to think of it. Okay, and so then we've got W. So then we got to pick one of these. And we'll say W minus, or W equals starting W plus the rate of change times the change in x would be x minus, sorry, I'm in a room, x minus 20 twelfths. So I'm using this point right here. My point is 20 twelfths, 27 twelfths. So I'm going to do the starting W 27 twelfths plus negative 0.25 times x minus 20 twelfths. That's like point slope form of a line. Any way you can make a line. So you just have to, any way you can make the equation of the line out of this, W as a function of x. There are many ways to do it. So one way is point slope form, which is y equals y naught plus m times x minus x naught, where xy is a point and m is your slope. So that's what I used. But if you have a different way of finding the equation of the line, it'll all be the same. So this thing right here, that's given an x, it gives you the corresponding w. So that's going to go here. So we won't go any further. We got everything we need except for the limits. So this is, I'm calling that star. So star goes right here. So because what does that do? Given a distance x, it gives you the width of your layer. The numbers are a little ugly, but the principle is the same as we've seen before. Okay, so now we're ready to set up the integral. Total work equals. So we're going to integrate from what to what? Not 0. The first layer is x equals 10 twelfths in feet. In feet, we need feet, right? And then the last layer is 20 twelfths of 62.5 times the length, which was that 52 twelfths or 13 thirds, times our width, which was our ugly formula down here, star, I'm calling it, times x dx. Okay, I hope the numbers aren't distracting from the principle of the setup, because that's the more important thing. Any questions on getting this one set up? Yeah.
Isn't 62.5 density not
No, it's weight density because it's pounds.
Yeah, weight density. And so when they were multiplied by the volume, and that gives us pounds, times the distance x gives us work in foot pounds. Is that right?
Yeah.
So it's this 62.5 is weight density times volume gives the force.
Yeah, I was thinking.
Okay, yeah, this one's in English. Other questions?
So if that was like a trapezoid, could you do like the area of a typical stroke of a trapezoid?
No, that's a lot harder. Yeah, I mean, so like,
Is that a trapezoid? I don't know.
well, this is a trapezoid, but your typical layer is just rectangular. You don't your typical layer. Just think of a really thin layer that we're going to lift up. What shape is that? Not trapezoidal.
Is there any way to do it like that? Almost just kind of like how you do with respect to the y-axis?
No, because if you do like a vertical slice,
Yeah.
no, that doesn't make sense because the top. So the whole point is we need a slice for which we can calculate the work. If you do a vertical slice, you can't calculate the work because the top water is going a shorter distance than the bottom water. So to do a typical vertical slice, you would need an integral, right? So then you'd be integrating a bunch of integrals. You see?
Yeah.
So you need an element such that you can actually calculate it straightforward, force times distance, and that's a horizontal slice because all the water goes the same distance. If you do anything that's vertical, then the water's all going a different distance. Well, that's the problem we have in the first place. Does that make sense?
It makes sense. I'm thinking of the cylinders now.
The cylinder.
How you were saying you can't do cylinders.
Yeah, you can't do a column of water. So like a trapezoid this way would be like a column of water. You can't. You would need an integral to do that. Okay, other questions about this one? Okay, so let's try a different. Like I said, like on the exam, you're gonna be faced with something new. So we got to practice seeing new things. So let's do hydrostatic force. Okay, this is another good example. Can I erase this? Like, please, right? Please erase it. Okay.
Basically, I just added in a 0 point, then I subtracted it out.
Okay, so hydrostatic force, so what happens is underwater, if you have some like vertical region, like a plate or a wall or something, so vertical plate, wall, etc. Then what happens is that the pressure on that thing varies with depth. The deeper you go underwater, the higher the pressure is. And so what does that look like? Pressure equals weight density times depth. So it's a function of like the density of the liquid and how far down you are. Okay, because like when you're down deep, basically the pressure is like all that stuff above you pushing down on you. So the higher the density is, the more pressure, and then the lower you are, the more pressure because there's more stuff above you. Okay, so weight density would be, that would be Newton per meter cubed, or pound per foot cubed. That's the same thing we saw before. And then depth would be meters or feet. So what are we saying? So P equals rho D. So that's basically what that's saying. Okay. So then the units of pressure would be what? If you take this newtons per meter cube or pounds per foot cube times meter or feet, then pressure has units, what? Would be newtons per meter squared or pounds per foot squared. So therefore, force equals what? How would we get force then from hydrostatic pressure? It'd be pressure times the area. And so if we want to total up how much force is on that region or on that vertical wall or plate, it's going to be a function of pressure, which is continually changing as you go deeper, right? So this again, this is perfect chance for an integral. And so if we want total force, what's the strategy going to be? We want a total force on R. So our strategy is going to be what? Yeah.
Area times the pressure.
Okay, kind of, but so just more broadly than that. More broadly than that. Yeah. Yeah, we're going to total up all the little bits of force. Okay, so just like before, we needed, when we were totaling up bits of work, we needed something we can calculate the work of, so that was like a horizontal layer. So what kind of elements on this plate are we going to select so that we can actually calculate a little bit of force? Is it going to be like a square? Is it going to be like a vertical strip, a horizontal strip, a triangle? What kind of element will we be able to calculate a little amount of force? So over that element, it's not nothing's changing. What will it be?
Is the shape like?
It could be anything. So that's its generic shape, but it doesn't matter what it is. Like a horizontal, but so this is flat this way. So horizontal, yeah, like a horizontal strip, right? A horizontal strip will be at all the same depth. So the whole strip will be at the same depth. So the pressure will be the same along that horizontal strip. But then as soon as we move down a little bit, we'll have a higher pressure. Okay? So the total force on R will be? I can do it fast. I can do it. What? The sum of little bits of force. Okay, the total force on R is going to be the sum of little bits of force, and those little bits will come in the form of horizontal strips because we can actually calculate there's no change in pressure across the horizontal strip. Okay, example. This one will have slightly easier numbers. Any questions before we look at an example? So find the total force on a triangular plate shown. Here's water. So the plate is this. It's a big plate. Okay. So I gave you the setup for what pressure and force is like, and now you've got to figure out how much total force on this plate right here, this triangular plate that's underwater. The top of it's 5 meters from the surface. It's 4 meters across at the top, and the height of it is a total of 8 meters. Pretend it's a test question. You've got all the tools. Can you do it? Okay, total force is going to equal what? Who thinks they got it? Someone, at least one. Total force equals what? Everyone should know this. This is not hard. The sum of little forces. If you want force, you need to sum up little bits of force. If you want work, you need to sum up little bits of work. If you want mass, you need to sum up little bits of mass. Okay? So, and what is our force? A little bit of force is going to be? Yeah.
I was gonna ask when you're drawing, is the triangle supposed to be like laying flat underwater?
No, these are vertical plates. The pressure changes with depth. This is the water. So ask that right away instead of this is the water. These are vertical plates. Pressure varies with depth. So the further you go down the plate, the more pressure is on the side of the plate. This is a vertical plate. Is that clear? Okay. All right, so how are we going to calculate a little bit of force? I just gave it to you. But what's the formula? Pressure times area. Okay, so a little bit of force is going to be pressure times area. Area of what? Horizontal strip. At a, so we'll go from the water level at a depth of x. Okay, so what is the area? The area is width times height. What's the height? Delta x. Okay, so that's our area. Width is going to be what? A function of x. We're going to have to set it up and do a function of x. It's a linear relationship. The farther the greater that x gets, the narrower w gets. So we're going to have this eventually. We're going to have, given an x, what's the corresponding w? This will be easier. When x is what? When x is 5, width is? When x is, what's the other one we know? 13. W is? 0. This will be easier. So then what is w for any x? You need to get that linear relationship. So it looks like -4, oh sorry, -13 W2 minus W1 over, so it's -1/2, right? -1/2. And then here, okay, so -1/2. Well, let's just do this one. 13, or 0 plus -1/2 times x minus 13. Again, so this w plus the rate of change, -1/2 times x minus 13. This is point slope form, right? Point that you know, slope or rate of change. Okay, so that's our W, negative 1/2 x minus 13. We'll go right there. That's our area. Width times height delta x. Okay, pressure. I told you how to find pressure. Pressure is weight density times depth. Okay, so what's the weight density? We're underwater. This would be 9,800, right? Weight density, so it'd be 9,800 newtons per meter cubed times depth is x. So the pressure is our weight density times x. Area is the width as a function of x times delta x. So that's our little bit of force, or I should be using delta right now. Okay, so now we're ready to write the integral. So we're going to sum up 9,800 times x times negative 1/2 x minus 13 dx, and x goes from first little strip of force we're going to calculate is at x equals 5. Last one is at 13. Yep. Does it make sense? Yes, sir.
Shouldn't the area be divided by or
No, because it's a rectangular strip, right? It's a little thin, just like when we did the just doing areas, right? We did horizontal strips and vertical strips. It didn't matter how it was curved or slanted in the big picture. It was just a rectangular strip. So it was always just the area of the rectangle. So when those get really, really thin, then the fact that the sides are sloped won't make any difference. Other questions? Yes, sir.
Describe weight density real quick. I don't really understand that.
Yeah. So for English units, weight density is 62.5 pounds per foot cubed. That's English. In metric, sometimes you have to have an extra step because they give you mass density, and weight is measured in newtons. So that's your F equals m times g. So English weight density is 62.5 pounds per foot cubed. In metric, mass density is 1,000 kilograms per meter cubed, but to get weight density, then you have to multiply that, this is kilograms, times 9.8 to get newtons. So it's 9,800. I don't know, am I asking you a question?
yeah, this is just for water, right?
Those are, right, water only. That's water only, that's right. Thank you for pointing that out. So this is only water. So did I answer the question? Yeah, so pounds and newtons are apples to apples. Pounds is weight or force in English. Newtons is weight or force in metric. But then sometimes in metric they'll give you mass, and you need to convert that to newtons. Okay, so we need to do one more important example. Well, you're free to go. If you want to slip out quietly, you're free to go. But this is all important for the exam. Any questions? Okay, here we go. Where's my problem? So this is going to be, we got.
Yeah.
Yep. All right, so we got an oil tanker. Okay, and it's filled with. Oil into there. Okay, that's the best oil tanker I've drawn all day. Okay, and so we got it's filled 3/4 full in height. And apparently this oil is blue. Okay, so the diameter is 12 feet. The length is 74 feet. And the fluid level is 3/4 of the height. Not by volume, 3/4 by height. Okay. 2 questions. Maybe I can grab it. What's the total force of the oil on the circular side of the tank? So the side closest to you that you're looking at there. And then 2, how much work would be required to empty Okay, what I also didn't tell you is that the density of gasoline is 44.9 pounds per foot cubed.
That's like a circle.
Yes, because it says circular in the description, not because of my drawing. But that's not a bad circle. Yeah, so it's an oil tanker, right? So it's circular or close enough. And so we want the total force on this surface right here, the total force on this surface. And then how much total work would be required to get all that oil out of an opening on the top of the tank, say up here. Okay, I think the best thing is for you guys to see if you can do it. Pretend it's a test question. Questions? So what we can do is I'm willing to stick around longer if you want to work on it, and then we can discuss it, and then at 7:15 or yeah, if you want to go, then you can go, but I'll stick around so we can finish these. But I think, like I said, the best thing is for you to try to do it in terms of getting ready for the test. Go. So for the pressure one, again, we're going to do our little strip there, right? Okay, so a little bit of force is going to be pressure times area. And the pressure is rho times d times the area. So what's our rho? It's easy, 44.9. Okay, what is d? D is this, to the top. Okay, so what is that? So this much from here to here is 6. Okay, so then what? And if positive y is up, then this distance here is what? No, it could be anything, right? So this is so it's going to be 6. But it's not going to be 6 plus y. It's going to be 6. This y will be negative, right? So you're going to need 6 minus y. Yes, sir.
Is the y going to the bottom of the circle or just to the rectangle strip?
It's just, you think of it as a coordinate system. So this is 0, 0. This is positive y going this way, and then positive x going this way. So you know your y's will be negative here, but you need a greater distance than 6, right? It's going to be this 6, basically plus the opposite of this negative value. So that's 6 minus y.
Yeah, but is it going? Because that rectangular strip is just a random strip.
Yeah, it's any strip. It's any strip.
So is y going to the bottom of the strip or to the bottom of the table?
Y is from the x-axis to the strip. This is y. It's the y coordinate from the x-axis to the strip. And then you're always going to add 6. But it's going to be the opposite of y. Okay? And then times, what's the area of the strip? Well, it's going to be delta y. It's going to be the height of it times, what? 2x. It's going to be 2 times the x coordinate. So we need x in terms of y. So the equation of this circle is x squared plus y squared equals 36. So we need to solve for x in terms of y. So it's going to be 2x is going to be 2 times the square root of 36 minus y squared. And we got it. Did you catch it? So the width of the strip is 2x, 2 times the x coordinate, and the x and y coordinates are related by the equation of the circle, x squared plus y squared equals 36.
What is the interval from?
All right, so we need to do that. So that's a little bit of work. Any questions on a little bit of work? Yeah.
Why is it 2x?
Because it's this whole distance here. See, that's 2 times x. Do you see it now? It's all the way from here to here, where this is the x coordinate. It'll be 2x. Questions about the little bit of force? Okay, and then we're going to sum all those up from y is going to go from -6 to +3. With a dy instead of a delta y. Ask me questions. Okay, so I want to clear up some confusion about the example at the end of class. So this is where we left this formula for a little bit of force of the strip like this. So this is actually incorrect. So I wanted to clarify and get you on the right track. So I went ahead and redraw the picture for the side of the tanker here, the circular side. So we got our x-axis here. We got our y-axis here. This point up here is 0, 6. And the height of the water is 3/4 of the height of the whole tanker, so that would be 3. I'm showing that here, 3 above the x-axis. So now I drew a typical strip here, and this could be any strip that we're going to calculate the force for. So if you notice, that strip is at a height of y above the x-axis, and that the level of the gas in the tank, the top level, is at 3 above the x-axis. So what we need to get to do the pressure calculation is we need the depth. So originally I was comparing this strip to the top, but really for pressure, 0 pressure is at the surface of the liquid, and so we want our depth to be down from the surface. So we really need this distance right here from the surface of the gas down to our typical strip. So that's why I called that D right there. So if the y coordinate gives us how high that strip is above the x-axis, and the surface level is 3 above the x-axis, then here's the setup for that. 3 up to the surface, y up to the typical strip, because it could be any strip, and then D would be that distance below the surface level. So then you'd see that D is this whole distance 3 minus that part y gives you D. So 3 minus y. So really, we had our weight density of the gas or the oil, 44.9, and then the depth, this is D for depth, below the surface is 3 minus y, and then delta y times 2x, because this is the x-coordinate from here to here is the x-coordinate, gives us delta y 2x, gives us the area of that whole strip. So really this is all correct, except we need to change that 6 minus y to 3 minus y, because we need the depth below the surface. And I actually did that, worked through that again. With the students, and so there it is. Okay, so that's the actual little bit of force on typical strip, and so then we're going to add up all the strips from -6, because we're looking at sort of for dy, the lowest strip that's going to apply a force onto this plate is down here at y equals -6, all the way up to the surface of the oil, +3. So from -6 to 3, 44.9, 3 minus y, 2 radical 36 minus y squared, which comes from x in our equation of our circle, times dy. And then I wanted to actually work out the problem for the getting all of the... Okay, so then actually I wanted to show an alternate way of doing this by changing the frame of reference. So I'm going to come in here and erase. Let's come back here. I'm going to come in here and erase and show you a different way that you might prefer. Either way is fine. So now I want to look at doing it this way. Putting our, if here's our, okay, so here's the side of the oil tanker. Again, the surface level 3/4 of the way up in height. So 3 feet from the center diameter, 3 feet from the top. So that's the radius is 6. So with another convenient way to set this up for doing pressure is to put your, kind of like what we've done before. So now I'm going to put my origin right there, and I'm going to make positive y down. and then positive x to the right. Okay, so that puts my circle, the center of my circle here. What, 3 feet below the surface of the liquid. So, and since this is positive y, that will actually be the coordinates 0, 3. So that's the center of the circle. But now my depth and the positive y coordinate are the same thing. How far down I am is exactly the same as y. So that is nice because now we can come over here and change this to 44.9 y. The depth is the same as y. Okay, so 44y, and then that's going to be the pressure, rho times depth, and the area is going to be, again, I have a typical strip here, in red. So my typical strip is going to have area, it's still going to be delta y here, and it's still going to be 2x. So this is x and x. So it's still going to be delta y and 2x, but now the only difference is the equation of the circle will be different because now our origin is up here, not in the center of the circle. So we need a center, we need a circle with center 0, 3 and radius 6, since the diameter is 12. So that's pretty easy. It's going to be x squared, x minus 0 squared, plus y minus 3 squared equals 6 squared, or 36. So now when I solve for x, it's going to be similar. It's going to be 36 minus this whole thing, and then the square root to get x by itself. So then this comes down here, and we change this to 36 minus y minus 3 quantity squared. So that's our x coordinate now because the center of the circle is at 0, 3, so we have to accommodate for that. And that gives us that equation of that circle. So then we have, so this makes the depth a lot easier to see because the depth is simply just the y coordinate because I put the x-axis at the surface level. So now whatever depth you're at, that's also the y coordinate because x is up here. So then the center of the circle is 0, 3. So it's going to be 44.9 times y. That's my rho times depth. That's my pressure. That's my pressure right there. And then times the area, delta y times 2x, where x is solving that thing for x. 36 minus y minus 3 squared. So with this new frame of reference, with my origin being here on the surface, x there and y there, this becomes little df. And then what am I going to do? I'm going to integrate from, now I'm going to integrate from 0. My first strip would be at y equals 0. And then my last strip would be at y equals 9. So I'm going to integrate from 0, first strip, all the strips from 0 to, this would be 9, because it'd be 6, and a whole nother radius down from the center. 3 plus 6 gives 9. So I'm going to integrate in this case from 0 to 9 df, or df is this right here, with a delta y, or with a dy instead of a delta y. Okay, so I hope that's helpful. You can choose either way to set that up. Okay, now I want to do the work to get all the oil out of the tanker. And so let me go ahead and just go to that here. So let's draw the picture again. Okay, and then this is going back this way. And we got D equals 12, L equals 74, and rho is 44.9. Okay. And now we're going to, and again, it's 3/4 full by height. So again, that's going to be 3 feet up. That'll be 3 feet up from this horizontal diameter, or 3 feet down from the top. And if our opening here is at the top like this, then in terms of the distance that we have to move every layer in terms of calculating the work, let's put our axis this way. So we're going to put kind of similar to what we did before with that last example with the pressure. So now that's going to be, again, positive y down, and then x to the right. And then this is going back into the page like this. And that's that distance of 74 feet back into the page. So we'll cut it off there, but we know that it's just gonna go back 74 feet back that way into the page. But in the screen here is our plane. It's going to be x this way and y down this way. Okay, so, and the reason I want to do that is now the distance that any layer has to move is going to be y again. By putting the origin at the height of the opening, now when we have our typical layer, we know it's going to be, work is going to be force times distance, so we're going to get the weight of that layer. The distance it's going to go is going to be the y coordinate. All right, so let's take a typical strip here. But it's actually not a typical strip. What is it? It's a typical layer of oil. So now now the 74 feet comes into it. And so we're going to have this layer of oil, and we've got to move it, a distance of y. So if we set that up here, so basically we have so it's going to look like that. That's going to be a typical layer, and so we need to find dW. dW is going, or delta W is going to be force times distance. That force is going to be the weight of that much oil, the weight of that horizontal layer of oil. So to get the weight, it's going to be the weight density times the volume. So the weight density is going to be rho times length times width times height. So that's going to be, because it's a rectangular layer, rectangular solid. So the force is density times volume. And now the distance, since I set my y equals 0 here, the distance it has to move is y. That makes that easy by putting that our origin at the place where we've got to get every layer to, then that distance that it has to travel is simply y. Okay, so we've got our 44.9. Okay, the length is our 74 feet. The width is 2x. And the height is delta y. Okay, so now what's x? So x is the x coordinate on the circle, just like in the last example, just like on the pressure part. So x is the x coordinate on the circle, and the width of our layer is 2x. Okay, so what do we need? We need the equation of the circle. Well, now if our origin is up here and positive y is this way, then that means our center of our circle is going to be 0, positive 12, positive 6. The whole diameter is 12. We're starting from 0 at the top. Now the center of the circle is 0, 6. And so the equation of the circle, center 0, 6, radius 6. That equation will be x minus 0 squared plus y minus 6 squared equals 36. And again, we need 2x. We need 2x, and so we're going to solve this for x. And so this is going to be our delta work. It's going to be 44.9 times 74. That's the length. The length of this way, that's the length. The width is 2x, so times 2. Solving for x here, 36 minus this, square root. Times the height of that. That whole thing is the volume. So length times width times height is the volume. Volume times mass density is the weight. So that's the force. The force to lift something is its weight. Okay, and then times the distance it's going to go. Now, because of the way we set up our system here, the distance it has to go is simply y. Okay, and then we're going to go, the first layer is going to be at y equals positive 3, and then the last layer is going to be at positive 9. So we're going to do the total work. It's going to be the integral from first layer 3, last layer 9 of dw, which is this thing right here with a dy instead of a delta y. Mass or weight density times volume gives force. The weight of an object is the force required to lift it. So this is the force that's going to be required to lift that layer. And then times the distance that we're going to apply that force gives us the total work, and the distance is simply y because we set up the origin there. So then from 3 to 9 of that. Okay, I hope it helps.